Hi Year 11 and welcome to our third lesson for the topic of arithmetic and algebra. In this lesson we're going to look at surds and indices. So far we've learnt about rational and irrational numbers, absolute value, expanding and factorising, and algebraic fractions. A surd is the square root of any non-square number. So for example, root 2, root 3 and root 5 are all surds, but root 4 and root 16 are not. Square root of 4 is 2, square root of 16 is 4, so they're both rational. But a surd can have a rational part as well as an irrational part. So for example, 2 root 7, the 2 is the rational part and the root 7 is the irrational part. To multiply surds, we multiply the rational parts together and the irrational parts together. So 2 root 3 times 3 root 5 is going to be 6 root 15. Now here's a special case. When we square a surd, well that's the same as root 3 times root 3, which is the square root of 9, which is 3. But can you see a shortcut to get from here to here? Well actually the square and the square root are opposite operations, so they cancel each other out. So we can just do this, and it's equal to 3. Here's one more. 2 root 7 all squared. Now in this case we've got 2 squared multiplied by root 7 squared. So 2 squared is 4, root 7 squared is 7, so the answer is 28. When we divide surds, we divide the rational parts and we divide the irrational parts. So 2 into 4 goes 2 times and 5 into 10 goes 2 times. The answer is 2 root 2. Now like algebra, we can only add and subtract like surds. So if I've got 2 root 7 and I want to add on another 3 root 7, I'm going to get 5 root 7. We might have a question like this where we've got different surds. So in this case, we're going to have root 3 take away 2 root 3. So that's negative root 3. And we've got 2 root 5 plus root 5, which is 3 root 5. So the answer, negative root 3 plus 3 root 5. Now sometimes we can simplify surds to make them alike. And to simplify, all we do is find the highest perfect square that is a factor. Remember, the perfect squares are 1, 4, 9, 16, 25, 36, etc. Or 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared. So suppose we want to simplify root 8. What is the highest perfect square that is a factor of 8? It's 4. So we rewrite 8 as a product of 4. Square root of 8 is equal to square root of 4 times 2. Now I encourage you to put the perfect square first. Now we're going to split this up. This is the square root of 4 times the square root of 2, and the square root of 4 is 2. So root 8 simplified is 2 root 2. Now if we wanted to add root 8 and root 2, we would change root 8 into 2 root 2 and then add, like this. Change it, and now 2 root 2 plus root 2 is 3 root 2. Let's have a look at some other common questions. Find the values of a and b if root 48 plus root 75 is equal to a root b. So we want to simplify both of those surds, add them together, and then figure out what a and b are. So let's start with the square root of 48. What's the highest perfect square that's a factor of 48? 4 goes into it, but it's not the highest one. 16 is. Let's rewrite square root of 48 as a product of 16. It's 16 times 3. So this is root 16 times root 3. So that's square root of 16 is 4. So there's square root of 48 simplified. Now let's do 75. The highest perfect square that's a factor of 75? Well, that's 25. Let's rewrite 75 as a product of 25, like that. Root 25 is 5, root 3. Okay, now we want to add those together. So square root of 48 plus square root of 75 is 4 root 3 plus 5 root 3, which is 9 root 3. What's a? Can you see? A is 9 and b is 3. We can use the distributive law to expand brackets. So if we've got root 3 outside of root 2 plus 1, we multiply root 3 by every term in the brackets. So root 3 times root 2 is root 6, plus root 3 times 1 is root 3. We can use FOIL as well. First, outer, inner, last. We get root 15, take away 2 root 3, plus root 5, take away 2. And that's actually the final answer. We can't simplify that any further. And just like with algebra, we have our special cases, perfect squares. So let's see if we can use the shortcut to expand this. We have root 2 all squared, which is 2. Take away 2 lots of root 2 plus 1. And then collecting like terms, we have 3 take away 2 root 2. And the difference of two squares. And remember, we need to do first and last. So root 2 times root 2 is 2, take away 1. Now this is an important result because with the difference of two squares, the answer is always rational. Which leads us nicely into our last part for surds, which is rationalising the denominator. Now we do this to make addition and subtraction of fractions easier. So if we want to rationalise the denominator of 1 on root 3, all we do is multiply top and bottom by this surd. So take that, multiply it by root 3 on root 3. Across the top gives us root 3, across the bottom gives us 3. And you can see how the denominator has become rational. Here's another example. Rationalise the denominator of 3 on 2 root 5. Now, to rationalise 2 root 5, we only need to multiply by the root 5, the surd part. So we don't need to use the 2. So we're going to multiply top and bottom by root 5, and then 3 times root 5 is 3 root 5, and 2 times root 5 squared is 2 times 5, and so our answer is 3 root 5 on 10. The conjugate of an expression has the same terms but a different sign. We saw this before with the difference of two squares. So for example, the conjugate of root 2 plus 1 is root 2 minus 1. You see? Same terms, different sign. Conjugates are important because you multiply them together, you get a rational number. We already had a go at this question here, but you might want to do it again. If we want to rationalise a binomial denominator, we multiply top and bottom by the conjugate. So here's an example, 1 on root 2 plus 1. We're going to multiply top and bottom by root 2 minus 1. And we follow the same rules as before. We want one lot of root 2 minus 1. And here we have the difference of two squares. And this is 2 take away 1. And so that gives us root 2 minus 1 all over 2 minus 1, which of course is 1. So our answer is root 2 minus 1. Example 2. Write 1 on 3 root 5 plus 2 in the form a plus b root 5 and find the values a and b. Okay, same method as before, we're going to multiply top and bottom by the conjugate. Now, before, when we had just a single surd on the denominator, I said you don't need to worry about the rational part. You can just multiply top and bottom by root 5. It's not the case with the conjugate. You need everything. If you just multiply top and bottom by root 5, take away 2, you won't rationalise the denominator. So, across the top, one lot of this gives us 3 root 5 take away 2, and on the denominator we have 3 times 3 is 9, root 5 times root 5 is 5, so 9 5's 45, take away 4. Now I'm going to split this into two fractions and put it in this form. So I'm going to put this root 5 at the end. It's going to be negative 2 on 41 plus 3 on 41 root 5. And so A is equal to negative 2 on 41 and B is equal to 3 on 41. Okay, one more example. Rationalise the denominator of root 2 minus 1 all over root 2 minus 3. So we're going to multiply top and bottom by root 2 plus 3. Now, important note here. We don't want to multiply top and bottom by root 2 plus 1, the conjugate of the numerator. That will actually rationalise the numerator, which is of no use to us. So, top and bottom by root 2 plus 3. Now, we've got FOIL we need to do here, and the difference of two squares here. So this is going to be root 2 times root 2 is 2, plus 3 root 2, take away root 2, take away 3, all over 2, take away 9. Okay, make sure that makes sense to you. We can collect some terms. So we've got 2 take away 3, which is negative 1, and we have 2 root 2 here, and this is negative 7. Right, important point. The minus is never put on the denominator in a fraction. So we are going to float this negative up. And it's actually the same as doing this, putting a minus in front like that. And so I'm going to just take that minus through the brackets, and I'm going to end up with 1 take away 2 root 2 all over 7. Okay, let's move on to our last part of this lesson, which is indices. And we'll start with index notation. Recall we write repeated multiplication in index form. This is the base, and this is called the index, the power, the order, or the exponent. And it means 2 times 2 times 2 times 2 times 2. The base number multiplied by itself a total of 5 times. Now there are 3 index laws. There's the multiplication law, so when we multiply pronumerals or numbers that are the same, we add the indices. There's the division law. When we divide pronumerals or numbers that are the same, we subtract the indices. And when we raise a power to a power, we multiply the indices. We also define the 0 index. X to the power of 0 is equal to 1. Let's look at some examples. Expand and simplify. So this first one we're going to do FOIL on. We're going to do first, which is going to be 3x squared y times x squared. So 3x to the power of 4y. Take away 2 times this, which is 6x squared y, plus x squared minus 2. And that's actually where we'll leave it. We can't simplify that any further. And this one, we can put it into 2 brackets, but let's try the shortcut. So this whole thing squared. Take away 2 times this, plus the last one squared. All right, I've done a little bit of working out here. So what is this going to be? 2 squared is 4. This is going to be x to the 4 because we're multiplying y to the 6. Take away 4x squared y cubed z plus z squared. Our negative index is defined as the multiplicative inverse. Remember, we were talking about x to the negative 1 being the reciprocal of x. In other words, 1 over x. So what do you think x to the negative 2 is? It's actually 1 over x squared. Now, a lot of people make this mistake, that x to the negative 2 is equal to 2 over x, but it's not. 2 over x would actually be equal to 2x to the negative 1. So it's just this part here that has the power of negative 1, not the 2. Now here's another question. What do you think 1 over x to the negative 1 is equal to? It's kind of the inverse of the inverse, if that makes any sense. It's actually equal to x. Have a look. 1 over x, which is the same as 1 divided by 1 over x. And let's keep, change, flip. It's equal to x. And fractional indices are defined as follows. X to the power of 1 over n is the nth root of x. So for example, 25 to the power of a half, well, that's the square root of 25, which is 5. We also have x to the power of m over n is equal to the nth root, that comes from the denominator here, of x, all to the power of m. Example, 8 to the power of 2/3. Well, that's going to be the cube root of 8, all squared. Cube root of 8, well, what number times itself gives us 8? Well, that's 2, and then 2 squared is 4. Okay, here's some examples. Write as a basic numeral 25 to the power of negative a half. So the negative means the reciprocal, 1 over, and the half means the square root. So this is the same as 1 over root 25, which is 1/5. Simplify fully and write in exact form. 8 to the power of a half divided by 2 to the power of negative 1. So this is the square root of 8 divided by a half. Now we won't be able to give a rational answer here because root 8 is irrational, but we can simplify it. Remember, this is the square root of 4 times 2, or 2 root 2. And then we're going to do keep, change, flip. So I've got 2 root 2 multiplied by 2, which is 4 root 2. And finally, write the following in index form with a denominator of 1. Again, I encourage you to stop the video and come back when you've had a go at these questions. Okay, let's look at these answers. The first one, we want to write this in index form. So the cube root, that's going to be x to the power of 1/3, and then we're raising it to the power of 4. So our answer here is going to be x to the 4/3. The next one, we just need to raise this up because we need a denominator of 1. So this is x to the power of 4, y to the power of negative 4. And then finally, we've got 2 pronumerals on the denominator here. So we need to bring the a up and then the square root of m up. So it's going to be a to the negative 1 and m to the negative a half. Okay, that's it for this lesson. Our next lesson is on equations.